average rates of change. And average rates of change are really just the slope between 2 points that you're looking at. So we you can't see anything. So our average rates of change are things that we could do before we ever took calculus. So what we're looking at today is we're going to be looking at instantaneous rates of change. So we, at the end of class yesterday, we came up with this limit definition of a derivative at a point. So I'm going to go back to this graph again. And so no matter what the equation is, like I've got this crazy equation here, but I could change it to something like x squared minus 3, make it a more simple equation. So, we have here, if we're wanting to have the slope between a point x f of x and some point a f of a, then we would just do slope formula. And so that was our f of x minus f of a over x minus a. And in order to make that the slope of the graph at that point, that slope of that tangent line, we would need our x to get closer and closer and closer and closer and closer to a. So that gives us our derivative that we're looking for. So let's do a problem with this. So I'm going to just write down again. You've got it on your notes where you might not be able to see it on my side. So the limit as x approaches a of f of x minus f of a over x minus a. That is our limit definition of a derivative at a point. Okay? So our point here, we want to find the instantaneous rate of change of f of x at t equals 3. So that instantaneous rate of change is the derivative, which is what we use this equation right here for. So we would want to plug in 3 for our a. So we would be finding the limit as x approaches a of, right now I'm just going to stick with f of x notation, but in a minute I'm going to replace that. And so if we're finding this limit, we need to plug in for our f of x. F of x here is just going to be the equation. So the square root of x plus 1. And then f of 3, to find f of 3, we would just plug in 3 into the equation. So that would give us the square root of 4, which is 2. So we would have minus 2. All over x minus 3. And I failed to replace my a with a 3 here. And so if I plugged in 3 right now, I'd get 0 over 0. So I cannot solve this just by direct substitution. So what do I have to do to solve a limit that looks like this? We will rationalize, in this case, the numerator, right? So we have to multiply by that conjugate. So we're going to multiply by x plus 1 plus 2 on the top and the bottom. And whenever I do that, I'm going to distribute here. Square root of x plus 1 times square root of x plus 1 is x plus 1. Then we'll have 2 square root of x plus 1 minus 2 square root of x plus 1, which cancels out, which is why we picked what we picked anyway. And then we'll have negative 2 times positive 2, and we'll get a minus 4. over x minus 3 times the square root of x plus 1 plus 2. Alright, here. Okay. Positive 1, negative 4, that's going to give us x minus 3, which is great. Because if I have an x minus 3 in the numerator and this x minus 3 in the denominator, then those are going to cancel. So now I can plug in my 3. So I'm going to get 1 over the square root of 3 plus 1 plus 2. And that's going to be 1 over the square root of 4 plus 2. So 1 over 2 plus 2, which will give me 4. Alright, and one of the things that they really want us to focus on, based on what they put in the new course outline, is really focusing on what this means in several different ways. So I could probably train you guys to use this formula over and over again, but they're not going to, there'll be a few questions on the exam where they might just ask you to do this, but most of it's going to ask you to apply and be more difficult questions. So let's look at this in Desmos just to see. I have created this beautiful graph right here, so it'll work for anything. So our equation was square root of x. Was it plus 1 or minus 1? Plus 1. Alright, so, and my a value was 3. So, oh, that's wrong. That moved the wrong one. Oh, because I was changing b. A needs to be 3. So, okay. So, right here is my point. If I wanted to, I could change that label now. That goes through the point 3, 2, right there. And we want to know what the slope of the tangent line is at that point. So when we do that limit, you can see here, we had plugged in our f of 3 was 2, and our x was 3. So basically what I was doing was finding the slope between the point 3, 2, and x, f of x. Because f of x is always y coordinates there. So I was doing f of x minus 2 over x minus 3 there. And so we're finding the limit as that x gets closer and closer and closer and closer to 3. And so right there, whenever, I don't think I've got it perfect, but right there at 3, we can see this line right here is going to have a slope, hopefully, of up 1 over 4. Might be a little off. No, it's all right. Up 1 over 4. Up 1 over 4. And you can see the slope of that line at that point. If we had been looking at a different point, let's say our A was down here. Let me change that label back to A, F of A. So if our point was down here, then you can see that our slope would have been steeper than that. So depending on where you're at, the slope will be steeper. But this can give you that slope at just that point. Okay, let's look at the next problem. Alright, so the position of a particle moving along the x-axis is given by the equation f of x equals x plus 1 squared. What is the velocity of the particle at t equals 1? So let's look at the graph of this one before we get started. So, what was that equation again? X plus 1 squared. So, x plus 1 second. And we want to know where t equals 1. So, on this graph, let me move that a value right there to 1. I'm going to change the label so we can see it better. 1. And then, what's the y coordinate there? 4. So we want f of x to get closer and closer and closer and closer to that point right there. Still, I can't get it. I think it was right. So 1, 4. We want it to get closer and closer there. And we're looking at the slope of this line. Just estimating, what do you think it looks like it is? We're looking at the slope of that black line. What do you think, Lily? Looks like it's about 4, because that'd be up 4 over 1. So let's, so that probably should be our answer. Let's figure, actually no, let's talk about why that slope is what we want. Let me put this in here. Way too big. So whenever we look at that graph right there, this graph gives me position. So if we're thinking of labeling these axes, this x-axis right here is position. I'm sorry. No, it's not. This gives us position, so the y-axis is position. And so it doesn't tell us any units here, but that's going to be a length measurement. So it could be feet, it could be meters, it could be yards, it could be inches, millimeters, something like that. And then the x-axis, that's time. There. So if we're finding the slope of this line, it would be our change in y over our change in x, which would be the change in position over the change in time. Right? So the slope in this case is change in position, which is, if that would be like if Wendy is here at time 2:01 and I let her walk to the office and she's at the office at 2:02. The change in position, that's her distance that she traveled, right? And then the change in time is the time that it took for her to walk that far. So, so this would be distance over time. So when we have a position graph, if we find the slope of that position graph, it's going to be a change in position over change in time, which is the speed, or it's actually not going to be just speed, it's going to be velocity of the graph. What's the difference in velocity and speed? Anybody know? What? No. They're like you could use them almost interchangeably in like everyday language. Like if you're just typically, like if anybody was going to want to use velocity in like just everyday language, I would think they were just trying to sound fancy, you know, like, oh, Destiny, your velocity is exceeding the posted speed limit, or you know, something like that. But velocity is a vector. Velocity has direction. So velocity is going to have a plus or a minus. So like if we're measuring velocity, it is either forwards or backwards, left or right. There's a positive and negative to velocity. It is still your speed, but with direction. Speed is just the magnitude of how fast you're going. It does not matter what direction you're going. So normally when we talk about how fast something is going, we usually talk about speed, because it does not really matter to the policeman whether you're going up the hill out here beside Pleasant Hill Daycare, or down the hill beside Pleasant Hill Daycare. If you're going 51 miles an hour, they're going to give you a ticket. So just speed is all you really care about there. So for this will give us velocity. So that would mean if the particle is traveling in the positive direction, you're going to have a positive velocity. And if it's traveling in the negative direction, you're going to have a negative velocity. So like in this case, we've got our little particle is moving on the x-axis. So the particle is either moving to the right or to the left for this. So in order to find the slope at this point, we're going to do that limit definition of derivative. So limit as x approaches a of f of x minus f of a all over x minus a. So we'll do, in this case, we'll do limit as x approaches. Justice, what's the a going to be for this one? Okay, so a is the fixed point that you are looking at. So we want to know the velocity of the particle at t equals 1. And actually, I should say x. That should say x, because the equation has x, not t. So at x equals 1. So right here at x equals 1, we're wanting to know the slope of the line at that point. So whatever x coordinate you have for that, that is your a value. So we're approaching 1 here. So that means we'll have f of x minus f of 1 all over x minus 1. So whatever point you're looking at, that is your a. And that would change if I wanted to see the velocity of the particle at x equals 2 or velocity of the particle at x equals negative 5. So f of x is x plus 1 squared, so I'll have the limit as x approaches 1 of x plus 1 squared minus f of 1. So f of 1, Cameron, what do we do to find f of 1? So we look at the graph, and where our x is 1, we look at our y coordinate, and what is our y coordinate here? It is 4. Now, let's say we did not have the graph, because these will be non-calculator sometimes. You won't have the graph there. So if I did not have the graph, the other way I could do that is I could just plug in 1 to my equation. So f of 1 would be 1 plus 1 squared, which would be 4. So either way, you'll get the same thing. If they have given you a graph, it'll save you a lot of time to get it straight from the graph. And then so that's over x minus 1. Ooh. How are we going to do this? Okay. All right, so whenever we do that, Destiny, what will we get? Right, x squared plus 2x plus 1 minus 4 over x minus 1. So we're just double squaring that x plus 1. And then we need to combine those like terms, so we'll have the limit as x approaches 1 of x squared plus 2x minus 3 over x minus 1. What do we do from here? Good. Factor. I'm embarrassed to say that when I was making these notes yesterday, I almost forgot how to do this problem. I was like, you can't do that. You can't multiply, go by a conjugate, or do anything. And then I felt very dumb whenever I realized that all we had to do here was factor. And you can factor into x plus 3, x minus 1. And we'll cancel those x minus 1s. So then we can just plug in our 1. So 1 plus 3 will give us 4. And that's what we said just looking at the graph. That was what we estimated our slope to be. And if you had this, problem, even if you were allowed to use Desmos, which AP exam does not use Desmos, I created all this extra stuff. You can see all those formulas. That's fancy looking right there, isn't it? Oh, that's impressive. But you have all those formulas. So, like, I created all that, so you guys would be just looking at, let's see, let's take these labels off. Just this. And so you would be looking at, oh, right here, oh, what is that slope close to? So it would be a little harder to estimate it so well. We estimated it perfectly whenever I had that line drawn in there. But you can at least kind of get a guess of what you think the slope will be there. But we do need to know how to do it by hand to get that more accurate answer there. Because our guess probably would not have been as good without that line there. All right, questions on 5? All right, so for 6, we'll have the graph, the function. I need you guys to change one more thing on these notes. I think that's a 0 right there. And I was not thinking very clearly whenever I put 0, because what's going to happen if I plug in 0 to this equation? Undefined, you got a vertical asymptote, so you can't find the slope of something if it's undefined at that point. So change that first one to a -1. Okay, and I think I used this notation before, F with the little tick mark behind it. Maybe. If I didn't, let's go ahead and address that now. F prime of x, we call that F prime of x whenever we read it, and it means the derivative of f at x, which also means the derivative is the slope of f at x. Okay. All right. So like, just to think of what it's asking us for here, this is asking for the derivative of f at x equals -1. And that word derivative, it just means the slope of that tangent line, that slope of that line that touches at one point. So let's look at the graph on this as well. So I'm going to change this to 1 over x is our graph. So we have this graph. We will be looking at the point let's make that one show back up. Label. It's not 1, 4 this time. It is 1, 1. So we're wanting to know the slope of the tangent line, or the slope of the line that would only touch at one point of that graph at, not at 1. We need to be at -1, don't we? Oh yeah, -1. Let's change that to -1. So we're looking at this slope right here. What would you guys, just looking at that, what would you guess that the slope is? If we were to draw in a line. What do you think, Justice? What do you think the slope? Negative something. That's good. Let's see. Let's just guess and see. Let me add something. Go down to the bottom. Let's see. Y equals know m has got to be negative. Let's change that y-intercept. That fits pretty nicely. I don't know if it's perfect. That might be perfect right there. It might have a slope of -1. That looks pretty close, doesn't it? There to only touching at one point. So when you're estimating that slope, you're kind of trying to think, well, if I had this line that just barely touched at one point, what would the slope of that line be? We definitely have a negative slope because this graph is decreasing here. So let's figure it out using the limit definition. So again, I'm going to write that limit definition up here. Again, the limit as x approaches a of f of x minus f of a all over x minus a. So for this one, I would be doing the limit as x approaches 1 over x minus, what is f of -1? If I plug in -1, what will I get there? -1, right? Or, yeah, -1. So f of -1 is -1 all over x minus -1. So that the limit as x approaches -1 of 1 over x plus 1 all over x plus 1. Okay, questions so far? Alright, for this we're going to need to get common denominators. So Lily, what would we do to get common denominators here? And just in that numerator. What? We can't just like divide it by x, but we could multiply the top and the bottom by x, so we'll have x in that denominator there. And so we'll have the limit as x approaches Alright, so we got 1 plus x all over x over x plus 1. Put some parentheses there. Okay, questions on that part? And then so dividing fractions is easy as pie. You can flip the second and multiply. So we would have 1 plus x over x times, this is x plus 1 over 1, so we'd have 1 over x plus 1. Alright, will anything cancel? So 1 plus x over x times 1 over x plus 1. Yeah, the x plus 1 and the 1 plus x can cancel. They aren't in the right order, but with addition, it doesn't matter, right? We can switch those. So now we've just got the limit as x approaches -1 of 1 over x, and we can plug in, so we'd have 1 over -1, and we would get a slope of -1. So at f prime of -1, the slope, or the derivative of f at -1 is -1. Okay. Now we've got to do the same thing. I really didn't leave enough room, did I? I can give myself more room. You guys cannot. You can go over to the side there if you need to. So for f prime of 1, we got to do the same thing, but we got to change all of our -1s to 1. So we've got the limit as x approaches 1 of 1 over x minus 1 over x minus 1. And so for this one, we're going to put this over 1. And so we got to multiply by x on the top and bottom to get common denominators just in that numerator part. So that is going to give us the limit as x approaches 1 of, we'll have 1 minus x over x minus 1. And dividing fractions is easy as pie. We're going to flip the second and multiply. So we'll have 1 minus x over x. And this is like x minus 1 over 1. So we'll have times 1 over x minus 1. Then we'll cancel here. It does not, because 1 minus x and x minus 1 are not the same. With the addition, we could cancel them. Here we don't have anything to cancel. But can we make them cancel? Is there something we can do so that we can get something to cancel? What can we do, Harper? Pull out a negative 1. So either one of these, I'm going to pull out a negative 1 out of this one. So this is going to be the limit as x approaches 1 of negative x minus 1 over x times 1 over x minus 1. And now those x minus 1s can cancel. And that's going to leave us with, don't lose your negative up here, negative times 1 gives you negative 1 over x. And if we plug in 1, negative 1 over 1 is also negative 1. Alright, any questions there? Oh, and we got one more to go. So for this last one, we've got f prime of negative 2. So that a this time is going to be negative 2. So we're going to have the limit as x approaches negative 2 of 1 over x minus 1 over negative 2 all over x minus negative 2. And I'm going to go ahead and change those signs. So I'm going to make this 1 over x plus 1 half over x plus 2 so I don't have those double negatives to worry about. Oh, and I'm not going to be lazy. I'm going to write my limit notation here. This time, Lakin, to get common denominators, we're going to have to do a little bit more. What are we going to have to do to that first fraction? Good. And what do we have to multiply the second one by? By x. So that is going to give us the limit as x approaches negative 2 of 2 plus x over 2x all over x plus 2. Okay? And dividing fractions is easy as pie. Flip the second and multiply. So 2 plus x over 2x times 1 over x plus 2. These will cancel. We get the limit as x approaches negative 2 of 1 over 2x, which is going to be 1 over 2 times negative 2. And we get negative 1/4 for our answer. Questions? Now, that last part was painful and lengthy, and I made it that way for a reason. To show you, I think that this formula this limit definition of a derivative formula. I think it's a little easier to understand than the one that we did a few days ago with the delta x. I think it's a little easier to understand. But you don't have to write this down necessarily, I just want you to watch. The other limit definition of a derivative was the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So that limit definition, if my f of x is 1 over x, if I do this, if I do the limit as delta x approaches 0 of 1 over x plus delta x minus 1 over x. So there I'm just plugging in x plus delta x here, and I'm plugging in just the equation here. Put this all over delta x. So I'm using that other definition. So if I do that, then it's harder to solve. I've got to multiply this by x plus delta x on top and bottom. I've got to multiply this one by x on top and bottom. And so that will give me the limit as delta x approaches 0 of x minus delta x. Make sure whenever you do that you distribute that negative with it, all over x times x plus delta x over delta x. And so the x's cancel right there, and dividing fractions is easy as pie, so I'll have the limit as delta x approaches 0 of negative delta x over x times x plus delta x. And that's like delta x over 1, so it's times 1 over delta x. And so those delta x's will cancel, leaving us with the limit as delta x approaches 0 of negative 1 over x times x plus delta x. Alright, so something's canceled here. We're going to plug in 0 for our delta x, which will give us negative 1 over x times x plus 0. So that's negative 1 over x times x. X times x is x squared. So I did all of that work. It's much harder, much longer, but now I know the derivative of f at x is negative 1 over x squared. So now, if I want to find f prime of negative 1, I just have to plug in negative 1 to that equation. And so I'd have negative 1 over 1, which would give me negative 1. And then if I want to find f prime of 1, I would plug in 1, negative 1 over 1 squared, which is also going to give me negative 1. And if I want to find f prime of 2, I would do negative 1 over 2 squared, which would give me negative 1/4, which you see are all those answers that we got. And then, if they asked us for other crazy stuff like f of 7, then we would have negative 1 over 7 squared, so we'd get negative 1 over 49. So if you have a problem like this, it is a lot more difficult to use that limit definition of a derivative at first, but you can plug in as many answers as you can plug in and find as many points as you want once you get that derivative correct. So we'll need to know how to use both of these limit definitions. So both of them are ones that we have to have memorized for this. So that concludes my demonstration there. So what I want us to do right